Have you ever wondered why e to the x is the only function that equals its own derivative? I mean, what is so special about this number e? It's defined in many ways, but today we're going to take a slightly different approach and we're going to define e from the one property that makes it truly unique, which is that it's the only number which can create a function that equals its own derivative, or in other words, it's the only base a for which the exponential a to the x equals its own derivative. And first of all, we're going to talk about why is the only function that can equal its own derivative an exponential in the first place. And then once we prove that, we're going to see that the number e is the only base a which can make that work. So for that single sentence, from that single requirement, we're going to derive e and we're going to show that it has to be an exponential. So let's get into it. So I just really quickly want to talk about what the derivative of a function actually looks like to show why e to the x is so special. For example, here we have a function x squared, and then its derivative function is 2x, and we call this function 2x the gradient function of x squared because this straight line tells us the gradient of our function x squared at any point. So for example, at x equals 4, over here I can draw a straight line. Here at x equals 4, our gradient function equals 8, which means where a function x squared, at x equals 8, at this point it has a gradient or a slope of 8, and we can test this out by drawing a tangent line, y equals mx plus b, where m is the slope and we're saying the slope is 8, and the c is just a constant that we choose. We can find it through algebra easily, and we can really see that at x equals 4 this function x squared has a gradient or a slope of 8, because we can see that this function, this green line, is really tangent to our function x squared. And this isn't special, any function, for example, x cubed, also has its own derivative, and that derivative is its gradient function. So for example, here at x equals 1, our gradient function has a value of 3, which means at this point over here, our x cubed function has a slope or gradient of 3. So any function has its own gradient function, but what makes e to the x so special is that it is its own gradient function. Because e to the x equals its own derivative, this function, the value of e to the x at any x, is actually the slope of the function at that point. So for example, at x equals 2, e to the x equals about 7.35. Well, that means that its slope here also equals 7.35. So if you draw a tangent, y equals mx plus c, m will just be e squared. It will be the value of that function at x equals 2. And now c is just a constant that we have to choose. You can find it through algebra easily, and now we can really see that when c is about negative 7.3, this function, this line really is tangent to e. So e to the x, it's an exponential function, but also the value of it will just always be its slope at that point x, and this is a really special property. Okay, so now we can actually start talking about why the only option for a function to be equal to its own derivative is an exponential. And here we're going to kind of assume that we already know what e is. You're going to see what I mean. But look, what we're just trying to say is that we want a function where its derivative equals the function itself. Or, in other words, we want f prime of x over f of x to be equal to 1 if I just divide on the other side. Now how do we kind of work with this piece of information? Well, I can think that the integral on both sides, so the integral of f prime of x over f of x dx equals the integral of 1 dx. And now I can use a substitution. I can say that u equals f of x, so that du equals the derivative of f of x dx. This is how you use substitutions. And now you can see that here the derivative of f of x dx, well, this would just equal to du, and this over here would just equal to u. So we actually get the integral of 1 over u du. And we know the integral of 1 over u, well, that just equals ln of the absolute value of u. And if we replace u with f of x, we get that this expression actually equals ln of the absolute value of f of x. This equals, well, the integral of 1 is just x, and then plus c, which is just a constant. And now if you put everything to the power of e, here we're already assuming that we already know what e is. This is just to see that exponential is really the only way, because look, we get, if we put e to the power of ln f of x, well, we know that this e and ln just cancel, so we get that f of x equals e to the power of x plus c. So we got that our function f of x, if we want this condition to hold, it has to equal e to the x plus c, where plus c is just a constant. This we can rewrite as e to the x times e to the c, and we can just rename this into constant a, so that f of x equals a times c. And this a also has a plus or minus, which I forgot to expand after the absolute value. But this, e times a times e to the x. So we can see that we get e to the x. It is the only way that a function can equal its own derivative because it's the only solution to this equation. But here we're already assuming that we know what e to the x is. How do we actually calculate e? How do we actually find out what e is? Well, now let's assume that we already know that this function will have to be an exponential. So now we can say that f of x equals a to the x. We know that that only an exponential function can be equal to its own derivative. And now let's actually look at the derivative of f of x using the definition of the derivative, which is just the limit as h goes to 0 of f of x plus h minus f of x over h. This is the definition of a derivative of any function, using first principles. And now, since f of x equals this, we can rewrite this as the limit as h goes to 0 of a to the power of x plus h minus a to the power of x over h. And now, because a to the x plus h is just a to the x times a to the h, we can factor out a to the x. We can factor out a to the x to get a to the h minus 1 over h. Of course, this is all in the limit. So now this will actually equal the limit. Well, this will now equal, let's take a to the x out of the limit because it doesn't include any h. So, a to the x will not be affected by this limit as h goes to 0. So we can take it out, and then we get times the limit as h goes to 0 of a to the power of h minus 1 over h. And now what is a to the power of x? Well, that just is our function f of x. So we got that the derivative of f of x equals f of x times this limit, which has a certain value. We can call it L times L. So now the only way that the derivative of this function equals its own value is if L equals 1. So we're basically saying that the only way this can hold is if the limit as h goes to 0 of ah minus 1 over h, well, this limit has to equate to 1. And if we can find an a such that this limit holds, then we can substitute this a that we find into here, and then we can say that this function truly is equal to its own derivative. So now how do we actually how do we work with this limit? Well, first of all, we can see that a to the power of h minus 1 has to equal to h as h goes to 0, because if they equal to each other, that's just going to equal 1. So, but we're looking at this before we apply the limit. So actually mathematically, if we want to be really correct, we have to say a to the h minus 1 is approximately equal to h. And if we actually want to work with this expression, we got to add an error term so that we can say a to the h minus 1 equals h plus epsilon of h, where this is just an error function or an error term which goes to 0 as h goes to 0. So now we can actually do work with this expression, because we can't really work with this. This is just a statement. This is an actual equality. So now we can say that a to the power of h equals h plus 1 plus epsilon of h, which is our error term. And now if you put everything to the power of 1 over h, we can see that a equals h plus 1 plus epsilon of h to the power of 1 over h. And now how do we actually get rid of this epsilon of h term? Well, we said that, we actually get the real value of a when we take the limit. We take the limit as h goes to 0, because, in this function, a is defined with the limit as h goes to 0 of this equality over here. This we said goes to 0. So we get the limit as h goes to 0 of 1 plus h to the power of 1 over h. That is what a has to equal. And lo and behold, if we say that n equals 1 over h, we just get that a equals the limit when h goes to 0. This goes to infinity. So the limit as n goes to infinity of 1 plus h equals 1 over n to the power of n. This is what a will equal. And if we actually express this limit, we get the value 2.718. We get the value, I think it's 8. We get the value of e. So we call this a. We don't call it a, but we call it e. This is how we define the number e, using that one simple sentence. Using that sentence that we want a function that equals its own derivative. If we know that it has to be an exponential function, using the definition of the derivative, we can get what a equals, and we see that a precisely equals e. So e is the number such that a to the x equals its own derivative. And now another interesting thing that we just found is also we know that whenever we have a function a to the x, if we take its derivative, df of x over dx, we know that the derivative will just be a to the x times ln x. This is a classic rule that you learned. That's the derivative of an exponential function. We saw that the derivative equals a to the x times this limit, or in other words, we kind of just showed that this limit equals ln x, which I think is also kind of clean. I never really saw ln x this way, but this ln x just equals to the limit as h goes to 0 of a to the h minus 1 over h, well, where this a is x in this case. Ln x is just the limit as h goes to 0 of x to the h. It's kind of clean. We kind of showed a new expression for ln x. We can actually see, where this comes from. But yeah, this is how we show what e actually equals to with that one simple sentence, with that one simple idea where we try to find a function that equals its own derivative, and we see that that function will be an exponential, and that value of a precisely has to be this value e. Thank you for watching.